Alright, gentlemen, we're going to do notes on Newton's third law of motion. Please remember, I do expect this to be in Cornell note style, so set it up in your notebook, whatever your next free page is. It's chapter 6. Alright, Newton's third law. Alright, you might list the law, and then I know there's going to come up the term action and reaction and a variety of other things that should be found here. Alright, so let's get to it. I'm going to pull up the PowerPoint. None of these are it. Let me open the right PowerPoint. Recent. There we go. Okay. Newton's third law. Newton's third law states, the one that you've heard before, for every action there is an equal and opposite reaction. For example, if you push on the wall with a certain amount of force, you get pushed back. The wall doesn't move. All right? If the action is equal and opposite, the wall pushes back with an equal and opposite force, thereby meaning you don't move and the wall doesn't move. Now, another example would be your book on the table. Your book is pushing down with 10 newtons of force. All right? Well, the table is pushing back up just as equally, putting this in static equilibrium. So if you think about it, if you're standing on a skateboard or a slippery floor and you push against the wall, you slide away from the wall because whatever force you apply to the wall is applying back and forcing you to move. Now, this is demonstrated a little more clearly when you jam your toe on a rock. When you kick a rock barefooted, it hurts. That's because you've applied force on the rock, but the rock in turn has applied force on your toe. Okay, so let's look at a problem dealing with this. A bug with a mass of 5 grams flies into the windshield of a moving bus which is 1,000 kilograms. Which will have the most force? Well, if you recall, let me pull up my pen real quick. There it is. Pen. If you recall, 5 grams is equivalent to approximately 0.005 kilograms. The difference in these masses is significant. What we're asking is which will have the most amount of force, the bug or the bus? Well, based on Newton's third law, the force will be the same. Notice the force stays the same while the mass gets very small, 0.005 kilograms. While the force, these are equal to each other, while the mass of the bus is 1,000 kilograms. Means the acceleration comparatively is much smaller on the bus as compared to the bug. But in the end, the force is the same. Action and reaction, depending on the different masses. Alright, consider you compared to the Earth. Your weight is very small. Your mass is very small compared to the Earth's mass. The Earth's mass is very large. So when you fall off this tower, your acceleration, we know, is 10 meters per second. Right? So action, the Earth pulls you down. The reaction is you pull on the Earth. Your mass is so small, the acceleration is insignificant comparatively. Another example is the bus tires push on the road, and the tires, or the road, pushes back on the tire, causing that friction or that movement. Another more clear example is when you are shooting out into space. The rocket fuel, the rocket pushes on the gases, which allows it to move, or the rocket pushes out the gases, and the reaction is the gases push on the rocket, causing it to move out into space. So, consider hitting a baseball with a bat. If you call the force applied the action force, so you swing your bat and it hits the ball, that's the action force. What is the actual reaction force? Is it the force applied by the bat, by the hands, the force applied to the bat by the ball, the force the ball carries with it in flight, or is it the centrifugal force in the swing? It is B, the applied force by the ball to the bat, and you can feel that in your hands when you get the reverberation from the bat. So let's review. Suppose you're taking a space shuttle walk, or you take your space shuttle out into space, and your safety light breaks. How would you get back? Well, the best way to get back is to remove items from your tool belt and start throwing them away from you, because whatever force you apply away is the equal amount of force being applied back upon you. This will help get you back to the space shuttle. Take a look here. We have a variety of laws here. The truck doesn't keep moving because an equal and opposite force is applied. Some of the force is lost as it gets transferred to the car. And then we also have inertia going on with the ladder. The ladder wants to stay in motion because it's already in motion. Alright, take some time and check out these crash tests. You may have to pull up the PowerPoint. I don't know if you can click on it through this website, but there are lots of crash tests that also show that equal and opposite amount of force. Okay, quick review. This goes over all of Newton's laws. So, things stay in motion unless acted upon by something else. Force equals mass times acceleration, and things, for every action there's an equal and opposite reaction. So if we apply this, Homer is large and has much mass, therefore he has great inertia. Friction and gravity oppose his motion. And Homer's mass times 9.8 meters per second squared, which is his force. And finally, Homer pushes against the ground when he falls flat on his face, and it pushes back. Alright, hope this helps. Feel free to go through it, skip through what you don't need, and pause on what you do need. Alright, have a great night. I expect to see this as a part of your notes. Thanks. Bye.